Good afternoon. I welcome you all to the session of hydraulic machines, and the topic of our today's discussion is the radial equilibrium of axial flow pump. In fact, in the last class we have tried to establish the mathematical expression governing the radial equilibrium condition of axial flow pump, and we have seen that if we try to cast this equation for two different cases, that is for incompressible flow and compressible flow, the different forms of that particular equation. And today, since in this particular course we are focusing mostly, rather not mostly, rather in this course is mainly designed to discuss the incompressible flow machines. I will be discussing the radial equilibrium equation pertinent to incompressible flow, and then we will try to discuss different cases. So, if we try to write the equation that we have derived in the last class essentially for the incompressible flow, and from there we will start our discussion. Okay. So, the radial equilibrium for the incompressible flow. Okay. So, if we try to write what is the equation? Equation is 1 by rho d p naught dr equals c theta square upon r plus, you can understand, half ddr of c theta square plus c z square. Note that here we are not going to consider CR because CR is 0 if radial equilibrium is attained. Now, this is the equation for the incompressible flow. We will now discuss different cases. Before we go to discuss this particular aspect, what I would like to discuss today, that a very common question is, why do we need to study this particular aspect? Though I have tried to discuss on this particular part in the last class, today again I am telling that if we try to recall, say if we try to write in this particular site, that if we go back to one of the previous classes wherein we have discussed about the types of pump, and then we have also mentioned the use of any particular type of pump in practical areas. So, if you try to recall, axial flow pumps are used in places wherein we require low head but high discharge. For example, for irrigation, mines. Now, it may be necessary that using an axial flow pump we may have to develop relatively higher head. That means, instead of lower head, in parallel to that, if we also need to develop moderate head from the axial flow pump, then what is done? Why I am going to discuss this particular part? Because you should know the purpose of studying this particular topic. So, if we try to write this axial flow pump, these are used for high discharge and low head, right. If we need to ensure that from using an axial flow pump, if we need to develop moderate head, then what should we do? So, basically from low head to moderate head, if we need to design an axial flow pump, what should a designer will do? So, basically discharge will be high and head also will be moderate. So, in this case, so that means for high cube and moderate H, what we need to do? We need to go for staging. So, that is called staging of axial flow pump. So, staging of axial flow pump is required when we need to have high discharge against moderate head, right. So, what do you mean by staging? So, now let us briefly discuss about staging over here. So, this is the equation that we have derived. Now, staging is, if we try to draw schematically, that will help you to understand what do you mean by staging. Now, what is staging? That is very important to understand. Say we have, right, this is, I am just drawing the, so if we have blades, okay, and if we design, now if we try to use different color to draw the, and rather to draw another set of blades like this. So, now this is called staging, in which, so this is, you can understand, this is 2 stage. So, this is 2 stage and this part is known as stator, while if we try to write using different color, now here this part is rotor. So, what is rotor? Rotor is rotating with shaft, rotor, that is rotating with shaft, and stator, that is fixed with casing. Okay. So, the stators are fixed with casing. So, this is casing. So, this is pump casing, while rotors are rotating with shaft. So, this is shaft and this will be rotating in this direction. This is say Z and this is R direction. Okay. So, this is rotating. Now, question is, here we have seen there are 2 different stages and this is essential if we need to have high discharge, that is fine, that will be definitely getting from the axial flow pump. In fact, axial flow pumps are designed to provide high discharge. Now, against this high discharge, if you would like to ensure that the head developed by the pump will be moderate, definitely you need to go for staging. Now, depending upon the requirement, should we go for 2 stages, 3 stages or multi stages, that depends. So, basically the sole purpose is to develop head using staging. Question is, if we need to go for staging, designing of stage, rather stage parameters. So, when you are going to design multi staging pump, axial flow pump, essentially to attain this condition, we need to know the stage parameters, flow coefficient, angles and also the blade angle. Now, all these stage parameters, that is the flow coefficient, distribution of axial velocity, distribution of pressure as well as flow angle, blade angle, etc., are obtained by studying radial equilibrium. So, why I wanted to discuss this particular part over here is that radial equilibrium is studied, rather radial equilibrium of axial flow pump is studied for the information about the stage parameters, which are very much needed when axial flow pumps are having multiple stages. Now, the stage parameters, that is flow coefficient, blade angle, flow angle, distribution of pressure, distribution of velocity, all these are obtained by studying the radial equilibrium. So, I hope it is now clear that this particular exercise that we have done in the previous class and again we are going to do in this class is very important for the design of axial flow pump, wherein multi-stage, rather I can say multi-staging is required to ensure that the head will be moderate against high discharge. Okay. So, now what I will do, I will be now going back to the main part of today's lecture is that using this particular equation, that is for the incompressible flow. So, this is for incompressible flow. Okay. So, now if we try to if we discuss, we will be discussing two different cases, that what will be. So, basically as I said just now, we need to know the stage parameters like velocity distribution, pressure distribution and other things. So, at least we will be discussing two different cases and we will try to discuss a few design parameters, stage parameters from the worked out problem. Okay. So, now first case is that if we try to discuss about free vortex flow. So, first case is that is very important, that is called free vortex flow. So, I will be writing the free vortex flow case 1, that is free vortex flow. So, what is free vortex flow? You have studied in fluid mechanics, free vortex, force vortex and Rankine vortex, we all have studied this. Now, for the free vortex flow, because ultimately if we try to recall, expression is 1 by rho dp naught by dr equal c theta square upon r plus half d dr of c theta square plus c z square, right. Now, radial equilibrium equation. So, there will be no velocity components in the radial direction, that is here. So, basically for the free vortex flow, what do we know? Free vortex flow, r into c theta equal to constant, say this is equal to k. So, this is for free vortex. Right. So, r c theta is equal to constant. So, that means if we try to cast this equation, so this is equation number 1. If we try to cast this equation in a different form, wherein we can plug in the value of r c theta is equal to constant and we will try to find out the distribution of pressure as well as the axial velocity. Okay. So, what we need to do? You can understand that this equation can be written by how? So, basically the right hand side, right. So, c theta square upon r plus d dr of c theta square upon 2, right, plus d dr upon c z square by 2. So, now if it is free vortex flow, so now I mean so this is the equation. So, this will be equal to 1 by rho dp naught by dr, right. Now, question is when p naught is not varying with r, that is what we have discussed in the last class, right. So, we have discussed in the last class that if p naught is not varying with r, right. So, if that is the case, so what will be the equation? So, if p naught is not varying with r, that will be equal to 0. So, that is when p naught is not varying with r, right. So, this is r. Okay. So, that means this is equal to 0. Now, I can write these two terms together in the form c theta upon r d dr of r c theta, right. So, I can club these two terms together and I can write in this compact form. Now, what I can write? I can write basically plus ddr of Cz square by 2 that is equal to 0. Okay. So, now question is what we can write? I can write this term that if I go to the next slide, we go. So, we have written C theta by r. If we go to the previous slide, C theta by r d dr upon C theta by r d dr of r c theta. So, d dr of r c theta plus d dr of C z square by 2 that equal to 0. So, now for free vortex flow this is equal to k equal to constant, that is what we have written in the last slide. So, we can write if it is constant then the first term is 0. So, we can write from this equation that is d dr of C z is equal to 0. So, d dr of C z square by 2 equal to 0, right. So, if that is equal to 0 then what we can write? C z square equal to say k 1. So, this is constant, right. So, basically you have seen if the flow is free vortex flow and total pressure is not getting changed along the radial direction, if P naught is getting changed along the radial direction, then we have seen that we can write the equation that is C z by r equal to 0. Okay. So, now that means what does it physically signify? It signifies that with respect to r C z does not vary. So, C z does not vary with respect to r. So, this is the conclusion that we are going to draw from this particular exercise, that C theta C z does not vary with respect to r. Now, basically here that is free vortex flow, Now, question is from this particular exercise what we can write if we try to have distribution of. So, if we try to write distribution of C z, so right. So, if we try to draw, this is the So, if we try to draw, this is the blade, just I am trying to draw on the upper half. Then if we take at least two different sections, right. So, here C z does not vary, so this is C z, right. So, if we take section A prime, this is C z, right, C z 1, and if we take section further downstream also we will find that this velocity is not varying, because C z is not varying. So, this is section B prime and C z 2. So, this is the rotation. So, this is the velocity distribution, that is axial velocity distribution we have obtained from this particular equation. Now, question is C z 1 not equal to C z 2, right, but at sections A prime and B prime, C z 1 and C z 2 does not vary with radius. So, basically it is not necessary that C z 1 will be equal to C z 2 and that will not be, but C z 1 is not equal to C z 2, it is not necessary, but at this particular section and this section C z will not vary if we go along the radial direction. So, this is the important conclusion. Now, what about, so this is a distribution of C z, and if we try to draw the distribution of C theta, then what will be distribution of C theta? You can understand if we try to write in the next slide. So, now distribution of C theta. So, we know that r C theta equal to k. So, this is free vortex flow. So, C theta will be equal to k by r, right. So, again if we try to draw the impeller and if we try to show only the upper half, this is the blade and this is rotating in this direction, then if we traverse along r, C theta will reduce, right. So, basically velocity distribution will be like this. So, you can understand. So, this is the velocity distribution. So, this is the velocity distribution of C theta, right. So, with increasing r, C theta will decrease. So, this is basically what we have obtained from this particular exercise. Okay. Now, you can understand this C theta profile. So, profile of C theta which changes with r, and this is hyperbola, hyperbola. So, this is hyperbola. Okay. Next, we will quickly work out if we now consider what will be the equation if we consider the force vortex flow. Okay. So, what is the force vortex? So, case 2 force vortex flow. So, I will be doing these two different cases, that is free vortex flow and force vortex flow. You can try what will be the distribution of velocities for the Rankine vortex. Okay. So, this is force vortex flow. Now, what is the equation? So, when P naught is not varying with r, then we can write equation that is C theta square upon r plus half d dr of C theta square plus C z square equal to 0, right. This is the equation we have seen. Now, when force vortex flow, then force vortex flow. So, that means what is the case? Force vortex flow, that means C theta upon r equal to constant. Say this is equal to k 2, right. I have used already k 1, so I am writing k 2, C theta by r equal to constant. So, if we try to cast this equation in a different form, then what can we write? So, we can write this equation that is just like the previous one, d dr of r C theta plus half d dr of C z square equal to 0. Now, C theta upon r equal to constant, therefore, C theta will be equal to r into k 2, right. So, if we try to plug in the value over here, then we can write this equation, that is k 2 and ddr of r square k 2 plus half ddr of c z square equal to 0. So, if we go to the next slide, so this is the equation I can write, very simple equation. I have used this relationship and I have tried to write this equation in this form. So, this is very straightforward. Now, if we go to the next slide, then what can we write? We can write, I mean this equation k 2 into ddr of r square k 2. So, k 2 then ddr of r square k 2 plus half ddr of c z square equal to 0. So, this is the equation that we can write. Now, see this we can write this equation that we can write d of r square k 2 square plus half. So, basically what we can write, I mean c z d of c z square by 2 equal to 0. So, that means we can write that c z square by 2 plus r square k 2 square will be equal to constant, right. So, this is equal to constant, say this is k 3. Okay. So, now c z will be equal to k 3 minus r square k 2 square, right. That is the equation. So, k 3 minus 2 into under root. So, this is basically the expression of c z. Okay. So, by doing this very simple calculation, we have arrived at this expression that c z is equal to 2 into k 3 minus r 2 square k 2 square under root. So, now question is, if we try to draw the distribution of flow velocities, that is very important. Now, you can understand. So, for the force vortex flow pattern, what we can see? So, now distribution of velocity, I mean velocity distribution, right. Cr equal to 0, Cz equal to under root 2 into k 3 minus r square k 2 square, right, and c theta will be equal to what we have assumed r into k 2. So, these are the expression of Cr, C theta, Cz. Now, as I said that if we try to, I mean radial equilibrium is studied to obtain the stage parameters, that is the distribution of flow velocities, then the flow coefficient and the different blade angles, I mean flow angles and flow angle and blade angle. So, basically what you can see from this particular exercise, I mean as compared to the previous case, if we go back to the free vortex flow, we have seen that Cz is not getting changed if we traverse at a particular section along the radial direction, right. But in this particular case, if we go to the next slide, that we can see at even at a given cross section, if we go up along the radial direction, Cz will decrease. So, basically I am writing that Cz will decrease with radius, right, and order is with the order of twice k 2 square r square. So, with this order of the magnitude of this order is this, with this order Cz will decrease with the radius, right. And what about c theta? You can understand c theta will increase with radius, and that is what we have seen. Now, as I said you that C theta C z that we have seen that two different cases, if it is free vortex flow or force vortex flow, then what will be the distribution of velocities, and from there we can try to, we can calculate the flow coefficient, we can, because I will be discussing, when I will be discussing about the maybe I will discuss about the degree of reaction for the axial flow pump, and there I will be discussing about that if we know the C theta C z, how can we calculate the degree of reaction, and basically if we need to go for staging of the axial flow pump, then the distribution of flow velocities, pressure, and the, as I said, flow angle, blade angle. So, information of these quantities will be very much required. So, basically to summarize today's lecture, what we have studied is that that we have tried to discuss about radial equilibrium. In the previous class we have established the mathematical expression governing the radial equilibrium condition. Now, today we have seen, rather we have briefly discussed about the objective of studying this particular aspect, and then we have tried to calculate, we have tried to investigate, rather we have tried to understand the distribution of flow velocities for two different cases. And as I said that you can take this task as an assignment, you can try the velocity distribution of velocity components for the Rankine vortex flow. So, with this I stop here today.